This is the second part of a series covering neural network models that do not use the backpropagation algorithm. In this video, we will look at Hebbian learning models with weight decay. This video was produced in Korean and then translated into English. The audio was generated by AI text-to-speech. In the last video, we looked at a simple Hebbian learning model and used it to perform simple pattern recognition. In this video, we'll look at a Hebbian learning model with weight decay, use it to perform the pattern recognition we did in the last video, and see what's different. Finally, let's use this to classify MNIST images. A simple Hebb's rule is not a convergent learning rule, since the weights continue to grow with each update step. In the example of the simple pattern recognition problem we looked at in the last video, if we repeatedly input the pattern X and Y into the Hebbian network and update the weights will continue to increase like this. This is a positive feedback loop. A large weight will produce a large value of Y, which will produce a large increase in the weight. To solve this problem, Grossberg proposed the Hebbian learning rule with weight decay in the 1960s. Weight decay acts as a natural regularizer, which helps to prevent the weights from becoming too large. There are two main types of weight decay. One is the Instar learning rule, and the other is the Outstar learning rule. Both learning rules were proposed by Stephen Grossberg in the 1960s. In the Instar learning rule, delta W is X minus W multiplied by Y. That is, W is updated as follows. Here, Wji is the connection weight between Xj and Yi. For example, W23 is updated as follows. W23 is the connection weight between X2 and Y3. In the Outstar learning rule, delta W is Y minus W multiplied by X. In the Instar learning rule, incoming weights of neuron converge to input pattern presented in the previous layer. In other words, the weights afferent to the postsynaptic neuron learn the input pattern X at the presynaptic neurons when the postsynaptic neuron is active. The neurons learn association between input vectors and their outputs. As W becomes closer to X, the expectation of delta W becomes 0, so W stops increasing. In the Outstar learning rule, outgoing weights of neuron converge to output pattern. In other words, the weights projecting away from the presynaptic neuron learn the output pattern Y at the postsynaptic neurons when the presynaptic neuron is active. The neurons learn to recall pattern when stimulated. We'll use the Instar learning rule to perform a simple pattern recognition. Next, let's interpret the meaning of the weight decay. The Instar learning rule can be written as follows. Here, Wt minus 1 is the weight of the previous step, and Xt and Yt are the input pattern and output of the current step, respectively. If Y is either 0 or 1, Wt can be written as follows. When Y is 1, Wt is updated like this. If y is 0, Wt is not updated and retains its previous value. This equation means that W is the moving average of x. Let's look at y. Let's say W is the simple average of x. Then, this can be written as follows. Here, this part is Wt minus 1, which is the average of x in the previous step. So this equation can be written as follows. Rearranging this equation, we get the following equation. This is another way to express the simple average. If we replace 1 over t here with the constant alpha, this becomes a moving average. This is the Hebb's rule with weight decay when y is 1. So from this equation, we can see that W represents the moving average of x. Now let's look at the geometric meaning of this equation. In step 1, the initial value of W is W0, and a data point x1 is input. This is the difference vector between vectors x and W. And this is the vector that is the difference vector multiplied by the scalar alpha. So by this formula, the vector W1 is updated like this. The W moves slightly closer to the data point x1. In step 2, another data point x2 is entered. This time the W moves here. The W moved along this path. If a new data point x3 is presented here, the W will move slightly in this direction. When multiple data points x are input, the W moves to the center of the data cluster. That is, the W moves to the average coordinate of the data points. Again, when an input vector is presented to the neuron, its vector of weights is updated in order to move it closer to the input, so that the neuron will respond more strongly when a similar input is presented. When several similar inputs are presented to the neuron, the weight vector converges to the center of the cluster formed by these inputs. This is similar to the k-means clustering algorithm. We can actually use this to do clustering tasks. We will discuss this in more detail later in the competitive learning model. This is also similar to the Rescorla-Wagner model of classical conditioning in psychology. We will not discuss this model here. Let's interpret this equation from a different perspective. The xt is a new data point, i.e., a new experience or a new stimulus presented to the input neurons. And the Wt-1 is the knowledge learned through the data x experienced so far. This is the difference between what the W knows from existing knowledge and what it learns from the new experience. We can call this surprise. When a surprise occurs, W is updated with new knowledge. Otherwise, W is not updated and retains its existing knowledge. Learning is all about surprise. In other words, we only learn when we are surprised. If what we expected happens exactly as we expected, we don't learn as much. Now let's look at the Hebb's learning rule with weight decay through a simple example. Let's feed these 3 patterns to this network and update W, like we did in the example in the last video. Each pattern is represented by an input vector x consisting of 9 elements. The output vector y is one hot encoded as follows. The input layer has 9 neurons, and the output layer has 3 neurons. The weights are a matrix with 9 rows and 3 columns. The initial value of each element is 0. Let's feed the first pattern into the network. We use this formula to update the 9 weights connected to the first output neuron. Subtract the first column vector of the weight matrix from the first input vector and multiply by the y value of 1. Then the first column vector of the weight matrix is updated as follows. We update the second and third column vectors of the weight matrix in the same way. Since the y values of the first pattern are 1, 0, 0, only the first neuron should be activated. Therefore, only the first column vector of the weight matrix is updated, and the rest are not updated. When we input the first pattern, the weight matrix is updated as follows. Next, we feed the second pattern into the network, updating the weights in the same way as on the previous page. Since the y values in this pattern are 0, 1, 0, only the second neuron in the output layer should be activated. Therefore, only the second column vector of the weight matrix is updated, and the rest retain their existing values. The weights are updated as follows. Finally, we input the third pattern into the network to update the weights. The weights are finally updated as follows. Since weight decay is applied, repeating this process does not increase W. Next, let's input the partially corrupted pattern into the trained neural network. When we input the vector x into the neural network, we get the following outputs. We use the softmax as the activation function. We can see that the first neuron in the output layer is most likely to be activated. So this pattern is most likely the letter T. For the second pattern, the third neuron is most likely to be activated, so it is recognized as the letter C. The third pattern is recognized as the letter U. Next, let's implement this example in code. The input data X is as follows, and the output data Y is as follows. Initialize the weights to 0. The weights are a matrix of 3 rows and 9 columns. This matrix is set to the transpose of the W on the previous page. Set the learning rate alpha to 0.1. Update the weights for each input pattern. We only need to update the corresponding row vector of W if an element of Y is 1. Repeat this process 100 times. The updated weights are as follows. You can see that W does not increase. We can normalize W like in the previous video, but if we use weight decay, we don't need to calculate normalization at every step. Next, let's input 3 partially corrupted patterns into the network. The output of the network for each pattern is as follows. When the first pattern is input, the first neuron in the output layer is activated. When the second pattern is input, the third neuron is activated. And when the third pattern is input, the second neuron is activated. Therefore, the first pattern is recognized as the letter T. The second pattern is recognized as the letter C. And the third pattern is recognized as the letter U. Let's run this code. We got the following results. Finally, let's classify MNIST images using weight decay. Load the MNIST dataset. X is the image data, and Y is the target label. Split X and Y into training data and test data. Initialize the weight matrix to 0. The weights are a matrix with 10 rows and 784 columns. Update as in the previous example. Once training is complete, we input the test data into the network and obtain the output values. We use the softmax activation function and argmax to transform the output values into one-hot encoding and measure the accuracy on the test data. The softmax outputs are as follows. The first and second test data points are most likely to be the digit 6. This test data point cannot be classified well because the digits 7, 8, and 9 have similar probabilities. In fact, this test data point looks like this. The accuracy on the test data was about 64%. The accuracy is lower compared to models that use backpropagation. However, considering that we used a single-layer network and a simple learning rule, we can say it's pretty good. We will later improve this significantly using a multi-layer network and contrastive Hebbian learning. Let's run this code. We got the following results. So far, we've looked at the Hebbian learning rule in 2 videos. In the next video, we'll look at the Hopfield network.